Well, we have been selling image sensors into the automotive camera market for more than 18 years now. So we have been around since the very early days when cameras got first deployed into the automotive market. Initially, of course, into the leading OEMs' high-end car models. Since then, we have done a couple of groundbreaking technology innovations, so driving the automotive camera and imaging technology forward. For example, we have pioneered and developed the split pixel technology for HDR imaging, which has become a standard now and is widely adopted in the market. Another example would be DCG, high dynamic range imaging, which we developed around 2015, which has even been going outside of the automotive market now into the high-end mobile phones, for example. On top of this, we had also programs dedicated to the automotive market, like our quality program targeting for 0 ppm, and we have spent great effort to push the camera performance across the whole automotive temperature range. Well, we already talked about the technology leadership, right? On top of this, I think the most important aspect is our broad product portfolio of image sensors going into the automotive camera applications. So we are basically catering to all the different application areas, be it rear view cameras, surround view cameras for human vision, advanced autonomous driving systems, or even in-cabin camera applications. On top of this, we are also addressing all the different segments within these application areas, let's say the high end, the mid, and the entry level. Moreover, we also have a dedicated ASIC portfolio, which is going along with our image sensors, which is solving dedicated processing or reception problems that our partners or customers would have. Well, omnisensing and omniviewing refers to the two main application areas that we had in automotive camera system. One is basically a human vision application like a rear view camera or a surround view camera, and the other one is a more computer vision application area, let's say a front view driver assistance system. Of course, today these two categories are converging, and a surround view system, for example, would also be used for scene recognition tasks. And of course, this all goes along with the big trends that we see in the automotive market, like electrification, the software-defined car architecture, and also autonomous driving. So going forward, to stay ahead of the game, of course, we will develop our products to cater to these new requirements of these new application segments. So we will, for example, add connectivity to our image sensors, which enables a much more efficient topology in terms of the software-defined car architecture. On top of this, we will also address other key issues which we'll see in the future, which is power dissipation, for example, of electronic components. So we will put some effort to improve power dissipation to make our chips more efficient, which helps the overall efficiency of the electric vehicles being sold in the future.
Yeah, one key technology clearly is high dynamic range. If you have sensors that do not support high dynamic range, you have to make choices about when you're driving in a tunnel, for example, you'll see clearly inside the tunnel, and outside of the tunnel, everything will be saturated. Or you could have the outside of the tunnel be clear, and inside of the tunnel will be very dark. So that doesn't work. So you need technology that addresses this. And then there's LED flicker. And these two go hand in hand in a way, because one technology to accomplish high dynamic range is to just change the exposure time and take multiple captures of the same scene with a different exposure time. However, at a short exposure time, you may not capture flickering LEDs correctly. And this is because LEDs do flicker. They flicker at a frequency that's not standardized, so we can't lock onto it. And so when you have a short exposure, sometimes your images may capture the LED. Sometimes the LED will be on when the sensor is not exposed. And so you'll completely miss that in your frame, and traffic signs will show up as incomplete. And that's obviously not a safe situation in traffic, so you can't have that. So you need a substantially long exposure to capture the LEDs during their on cycle without saturating. So that's the key with HDR. Then there is, aside from HDR and LFM, which are very critical to look outside of your vehicle, we have in-cabin applications as well. And for those applications, one very important technology is our TheiaCel global shutter capability. So with TheiaCel, we have about 4 times the QE of conventional solutions. And this helps our customers to burn less power or to use fewer LEDs, which reduces the cost of their overall system. So those are a couple of key technologies out there that help us serve our customers. All right, so we talked about HDR and LFM, and so what we need for HDR and LFM is a long exposure time, but not saturated. So one way to do this is using our split pixel technology, and this has served us very well over the last few years. But as we wanted to shrink the technology further, we recognized that maybe the split pixel technology is not the best technology to support further scaling. And so we reached out to use low-fit technology in combination with the dual conversion gain technology we already introduced in 2016 to the automotive market. So DCG allows us to capture images with both a high conversion gain for low noise but saturate quickly, and low conversion gain with higher noise but we can saturate at a later point in the scene. However, DCG is limited still by the full well charge in the photodiode. So to overcome that limitation, that's where low-fit comes in. So when the photodiode is full, charge from the photodiode will overflow first into the floating diffusion on the pixel, and then into the low-fit capacitor, which can hold about 100 times as much charge as our floating diffusion. Now we have a technology where we can capture a high dynamic range scene with an exposure time long enough so we can capture these flickering LEDs in a single photodiode, in a single exposure. And so while DCG is not new and low-fit is not new, what sets TheiaCel apart is that we were very good at implementing this. So one problem is with low-fit that, as I mentioned before, we are essentially integrating our charge on the floating diffusion and the low-fit node. And so leakage on these nodes cannot be distinguished from photocurrent. The leakage on these nodes is relatively high, typically, and will be different from pixel to pixel. So this leads to an effect known as dark signal non-uniformity. And at higher temperatures, this becomes pretty bad. And as such, it will start to affect the so-called knee point SNR, which we get when we transition from the DCG readout to the low-fit capture. And so where TheiaCel stands out is that we managed to improve this knee point SNR by decreasing the DSNU quite dramatically and optimizing the photodiode full well charge, which signifies the point where we have to switch from the DCG capture to the low-fit capture. Doing all this, we managed to achieve a 26 dB SNR at the knee point at 125 degrees centigrade and 22 milliseconds of exposure. Most of our competing technologies out there only manage to accomplish those numbers at, let's say, 11 milliseconds exposure, or even at lower temperatures like 105 C. So what this really means is, in low light conditions, when you want to increase the exposure time and you have a competing technology, you'll get stuck at 11 milliseconds, or you'll get stuck at 105 C. we can double the exposure time and have 125C operation. And this also helps to improve the low light performance. So there's no excuses. There's no, we have to prioritize dynamic range or SNR. You get both in the same package. And that's why TheiaCel stands apart. So we went and integrated this TheiaCel pixel in 8 megapixel sensor, the OX08D10. And so this has a 14K full well on the photodiode, a 650K full well on this low-fig capture. We have the best sensitivity in the industry, a very low PRNU, 0.6%, a 0.6 electron read noise. And so with this, we got in 4 captures, the ECG, low-fig, and the short exposure. We got 113 dB of single exposure dynamic range, flicker-free, and 140 dB in total. And all this with an 11 millisecond exposure, 30 dB SNR at 125C. And 26 dB, which is kind of recognized as the target to reach at 22 milliseconds. This is absolutely unique in the industry, and so we're very proud to announce this.